Dear students, Assalamu alaikum. Hope all of you are in sound position with your family members. Here is Aydin Parveen with Chemistry First Paper online class arranged by KPB School and College. Today, I would like to discuss ionic product of water, pH of solution and pH scale, dissociation constant of acid and base, and lastly, buffer solution and buffer action. At first, I would like to discuss ionic product of water. Look here. This is the equation of ionization of water. And according to law of mass action, we can write Kc equal to molar concentration of hydrogen ion into molar concentration of hydroxide ion divided by molar concentration of water, or Kc into concentration of water equal to molar concentration of hydrogen ion and molar concentration of hydroxide ion. And here water is a weak electrolyte, so pure water ionized very small amount, that is concentration of water is constant. So the product of two constant, that is Kc and concentration of water is represented by another constant Kw. So Kw equal to concentration of hydrogen ion and into concentration of hydroxide ion. And here Kw is known as the ionic product. Its value changes with the change of temperature. Ionization of water is an endothermic process. So Kw of water increases with increase of temperature. And increase in temperature. And since the value of Kw, look here, the value of Kw equal to 10 to the power inverse 14 at 25 degrees centigrade temperature, we can write concentration of hydrogen ion into concentration of hydroxide ion equal to 10 to the power inverse 14, or concentration of hydrogen ion equal to concentration of hydroxide ion equal to 10 to the power inverse 7 in case of pure water. And in case of acidic solution, concentration of hydrogen ion, that is concentration of hydrogen ion is greater than concentration of hydroxide ion. And in case of basic solution, the concentration of hydrogen ion is less than concentration of hydroxide ion. And in case of neutral solution, the concentration of hydrogen ion and hydroxide ion is equal. Whatever may be the nature of water, that is, it may be acidic or basic, the ionic product of water is constant at constant temperature, and it is Kw equal to 1 into 10 to the power inverse 14 at 25 degrees centigrade temperature. Now I would like to discuss pH of a solution. The negative logarithm of the molar concentration of hydrogen ions in a solution is called pH of that solution. And we can express pH mathematically, that is pH equal to minus log concentration of hydrogen ion. And the higher the concentration of hydrogen ion, the lower the pH. That means if the concentration of hydrogen ion is higher, then the value of pH is lower. The decrease of pH by 1 unit means the increase of hydrogen ion concentration by 10 times. Similarly, an increase of pH by 1 unit means the decrease of hydrogen ion concentration by 10 times. Similarly, we can express the concentration of hydroxide ions by POH equal to minus log concentration of hydroxide ion, and at 25 degrees centigrade temperature in a neutral solution, the concentration of hydrogen ion is equal to the concentration of hydroxide ion. That is, the pH equal to POH equal to minus log 10 to the power inverse 7, that is 7. That means the pH of neutral solution is 7. And pH of basic solution is greater than 7, and pH of acidic solution is less than 7. Now I would like to discuss pH scale. pH scale is introduced by Sorensen, a Scandinavian chemist, in 1909 to express hydrogen ion concentration. The scale by which the acidity and basicity of a solution can be determined with pH value is called pH scale. The pH range of pH scale is 0 to 14. Look at the figure, please. Look at the figure, please. Here, this is a pH scale, and here pH value for neutral solution. pH value for neutral solution is 7, and you see the pH value of water is also 7. And if we add some acid to water, the concentration of hydrogen ion increase due to the dissociation of acid, and pH of that solution decrease below 7. That means then the solution will be acidic. If we add some acid to neutral solution. And on the other hand, if some base is added to water, that is neutral solution, the concentration of hydroxide ion increase due to the dissociation of base. So pH of that solution increase, that is pH of that solution is alkaline or basic, and it is above 7. Therefore, if pH is 7, we can say the solution is neutral, and if pH of a solution is less than 7, then we can say the solution is acidic, and if when the pH is greater than 7, we can say the solution is alkaline or basic, and the value of if the value of pH is more greater than 7, that is 12 or 13 or 14, then these are the strong base. And on the other hand, if the pH value of a acid is 3 to 1, they are the strong acid. And you look here another figure, this one, there are some pH values of some common substances. Look here, the pH value of distilled water is 7 and pH value of urine is 6, that is slightly acidic, and pH value of tomato black coffee is 5, it is also acidic, and pH value of tomato juice is 4, this is an acidic solution, and pH value of orange juice is 3, it is also acidic solution, and lemon juice is 2, that is, and gastric acid where HCl is present is pH is 1 and it is a strong acid. On the other hand, the seawater's pH is 8, that is above 7, that means it is alkaline, and baking soda pH is 9, and milk of magnesia pH is 10, that is they are basic or alkaline solution, and ammonia solution pH is 11, whereas bliss which pH is 13, and this is strong base. So these are the pH scales by which we can identify the pH of different solutions to compare their color. Now I would like to discuss the dissociation constant of acid. The fraction of the number of mole of an acid dissociated in per liter aqueous solution is known as dissociation constant of acid. Here this is the equation of dissociation of acid, and according to law of mass action we can write Kc equal to hydrogen ion concentration into concentration of A ion divided by concentration of Ha and into concentration of water, and K into concentration of water equal to concentration of hydrogen ion into concentration of A ion divided by concentration of Ha. And since water is present in a larger quantity, its concentration remains practically constant. So, constant with K give, so the constant with K constant give another constant which is denoted by Ka, and Ka equal to concentration of hydrogen ion into concentration of A ion divided by concentration of Ha ion. Here Ka is dissociation constant of acid, and the larger the value of Ka is, higher is the concentration of hydrogen ion. Therefore, stronger is the acid. That means if the hydrogen ion concentration is more, then we get a larger value of Ka, and then we say this acid is stronger. So, knowing the dissociation constant of acids, their relative strengths can be compared. Now I would like to discuss dissociation constant of base. The fraction of the number of mole of a base dissociated in per liter aqueous solution is called dissociation constant of base. Look here. This is the equation of dissociation of base. Here BO base dissociated into B plus and hydroxide ion, OH minus ion, and according to law of mass action we can write K equal to concentration of B plus into concentration of hydroxide ion divided by concentration of BOH into concentration of water, and K into concentration of water equal to concentration of B plus ion into concentration of hydroxide ion divided by concentration of BOH. And here water remains constant, so this constant with K give another constant that is Kb. So Kb equal to concentration of B plus into concentration of hydroxide ion divided by concentration of BOH. This is the dissociation constant of base, that is dissociation constant of base is represented by Kb. The larger the value of Kb is, higher is the concentration of hydroxide ion. That means if the concentration of hydroxide ion is large, then we get a larger value of Kb, and then we can say the base is strong. So, knowing the dissociation constant of bases, their relative strengths can be compared. Now, I would like to introduce another topic, buffer solution and buffer action. The solution whose pH remains unaltered even after addition of a small amount of base or acid is called buffer solution. The strength of a solution to prevent the change of pH is called buffer capacity of the solution, and the mechanism of prevention in change of pH value even after addition of acid or base is called buffer action. There are two types of buffer solution. One is acidic buffer solution and another is basic buffer solution. The acidic buffer solution contains a weak acid and its conjugate base solution. On the other hand, basic buffer solution contains a weak base and its conjugate acid solution. Now, I would like to discuss mechanism of buffer action of acidic buffer solution. An example of acidic buffer solution is mixture of acetic acid and sodium acetate. Here, acetic acid is weak acid and it dissociated partially and produces acetate ion and hydrogen ion. On the other hand, sodium acetate dissociated completely and produces sodium ion and acetate ion. Here, the buffer has three ions, that means acetate ions, hydrogen ion and sodium ion. Now, if a small amount of acid is added from outside, that means hydrogen ion concentration is increased. If we add some acid from outside, then hydrogen ion concentration is increased, and this hydrogen ion then react with acetate ion and produces acetic acid to neutralize the pH, produces acetic acid. As acetic acid is a weak acid and there is acetate ion present in the buffer solution mixture, that means acetate ion is already present in the buffer mixture, acetic acid will not ionize. that is, the newly formed acetic acid will not ionize due to the common ion effect, and the value of pH will not change in this case. And on the other hand, if we add a small amount of alkali in this buffer solution, then hydroxide ion concentration, look, hydroxide ion concentration is increased, and to neutralize the pH value, this hydrogen ion reacts with hydrogen ion. This hydroxide ion reacts with hydrogen ion and produces water, which is a neutral substance. So the value of pH of solution remains unchanged. So it is clear that in acidic buffer solution, if you add a small amount of acid or base from outside, the pH is not changed. Now, lastly, I would like to discuss mechanism of the buffer action of basic buffer solution. An example of basic buffer solution or alkaline buffer solution is a mixture of ammonium hydroxide and ammonium chloride salt. Here ammonium hydroxide is weak base, and it is ionized partially and produces ammonium ion and hydroxide ion. On the other hand, ammonium chloride dissociated and produces ammonium ion and chloride ion. So here the buffer solution contains 3 ions, that is ammonium ion, hydroxide ion and chloride ion. Now if we add a small amount of acid in this solution, that means then hydrogen ion concentration is increased due to the dissociation of acid, then it will react. Then this hydrogen ion will react hydroxide ion in the solution and produces water to neutralize the pH. The neutralization of hydroxide by added acid is compensated by dissociation of weak ammonium hydroxide. And again, if we add a small amount of alkali, that is hydroxide, then hydroxide ion is increased due to dissociation of alkali, and then it reacts with ammonium ion to produces ammonium hydroxide, and ammonium hydroxide is weak base. It remains undissociated because already ammonium ion is present in the solution. So the newly formed ammonium hydroxide is undissociated. That's why there will no change in the pH of the mixture. So we can conclude that the basic buffer solution, in basic buffer solution, if you add some acid or base, whatever it is, it doesn't change its pH. I think all of you understand the topics very clearly. Hope all of you practice mathematical problems related to discussed topics. No more today. Stay safe. Take care. Bye.